The next section of our review on integration covers integration by splitting, which is really not a formal, method, but it is a technique that we use. And the idea here is just that when you have a large fraction, a rational expression, or if you have an integrand that's made up of multiple parts that are added or subtracted, often it makes sense to split it up and split it into smaller integrals. So we'll do a couple examples of those. So this is the first example. This is definitely something that we covered in the first year calculus course, but it may be something that you forgot about. The idea is that when you have a rational expression like this that has, like a larger polynomial on the top and one term on the bottom, one thing that we can do is we can effectively split this into smaller fractions, right? I can make this the integral of x cubed over x minus 5x squared over x plus 3 over x dx. And the idea is that each one of these things can individually be simplified. This would give me the integral of x squared minus 5x plus 3 over x. And then all we have to do is evaluate each of these antiderivatives individually. This shouldn't be difficult for you to do, so pause the video for 30 seconds and take this antiderivative. So the integral of x squared gives me 1/3 x cubed. The 5x becomes minus 5 halves x squared. And then this last one, hopefully you remember that the integral of 1 over x is natural log of x. So we're going to get plus 3 times the natural log of the absolute value of x. And then we have our plus c on the end. Right? This is a problem that we would not otherwise have known how to do, and it just comes down to, when you have an expression like this, polynomial on top, monomial on the bottom, it's very, very common that this is the strategy. You split it into separate pieces and do the integrals individually. So my next example is a little bit different, right? And the thing I really want to highlight here is this integral does have two parts. There's the x squared part, and then there's the x over 3x squared minus 1 part. Right? And man, I'd recommend, pause the video for a minute, sort of think about this for a minute, and think about what you might need to do. What I hope you were able to come up with is that u substitution looks like it might help. If I made this my u, the derivative of that is 6x, and that's what I have on the top. And this is the key part. I agree that this needs u substitution, but this doesn't. In fact, if you try and do this u substitution and fit x squared into it, it will probably get messy and ugly. So what you're going to want to do here is split it into the integral of x squared dx minus the integral of x over 3x squared minus 1 dx. Right? This first black integral is easy, right? This is just 1/3 x cubed. Right? The other one is going to require u substitution. So I'll choose my u to be 3x squared minus 1. My du will be 6x dx. Right? From here, you guys should know what to do. As I'm working these steps out, you should already know what I'm going to be doing next. Right? I'm going to solve for dx. Get the dx is du over 6x. When I substitute those things in, x over u times du over 6x. Surprise, surprise, these x's drop out of the problem. This is still just 1/3 x cubed. I mean, we've been done with that part for a while now. Minus, and then I'm just going to pretty this up. This is 1/6 the integral of 1 over u du. And at this point, we're really close to being done. We have 1/3 x cubed minus 1/6 the natural log of the absolute value of u. And I'm going to skip a step here. We might as well just substitute our value back in. This was 3x squared minus 1 plus c. And this is our complete answer. Right? The key thing to remember here is that sometimes a problem requires u substitution, but only for part of it. And so if those parts are separated by an addition or subtraction, you can totally split it into two separate integrals and just work them out individually. Sometimes they'll need a u substitution and not. Sometimes you'll have two parts that both need different u substitutions, and that's fine. You can work them out for each integral individually. So I mentioned previously that some integrals like this, where you split them into two parts, are going to require two different u substitutions. So this one here is going to require a 2x, this one here is going to require 3x, although I suppose in both cases we can probably get away with using the shortcut method. At any rate, pause the video, work through this problem, sort of make sure that you can do the integral, and then also evaluate using the bounds, the pi over 6 and the 0. So work that out now, then we'll check our answers. So in this case, because these both have the argument has a derivative that's constant, I don't really need to use u substitution, so I'm just going to work through the integrals of these things. The antiderivative of the sine of 2x is negative 1/2 the cosine of 2x. And I'll have minus. Now the antiderivative of cosine 3x is 1/3 the sine of 3x. And then this is evaluated from 0 up to pi over 6. And hopefully you remember how we work with this. We plug in the pi over 6 first and then the 0. So when I evaluate for these things, I'll have negative 1/2 times the cosine of 2 times pi over 6 is pi over 3, minus 1/3 the sine of pi over 2. So it'll be all that minus, and now I'll plug in 0. This will be negative 1/2 the cosine of 0 minus 1/3 the sine of 0. And we're just evaluating at this point. The cosine of pi over 3 is root 3 over 2, so that's negative root 3 over 4. Minus the sine of pi over 2 is 1, so that's just minus 1/3. Then we have minus. So let's hear the cosine of 0 is 1, so that's negative 1/2. And the sine of 0 is 0, so minus another 0. So 0, not a 6. Great. So at this point we're sort of just combining the parts that are similar, right? We've got negative root 3 over 4 minus, this will be 2/6 plus 3/6. So I'm looking at a final answer here of 1/6 minus root 3 over 4.